Hello everyone, my name is Kaiji Zhao and I'm a PhD student at Texas A&M University. Today I will be presenting on a paper titled Unsupervised Machine Learning via Transfer Learning and K-means clustering to classify materials image data. This work was published on a journal named Integrating Materials and Manufacturing Innovation, and it was authored by Cohn and Dr. Elizabeth Holm. This paper focuses on how unsupervised machine learning techniques can be applied to classify images of materials, specifically leveraging transfer learning combined with K-means clustering. Unsupervised learning offers several advantages and is worth researching, particularly in scenarios where labeling data is costly and challenging for humans. This is especially useful when dealing with large data sets where labeling each item would be highly time-consuming or difficult to define. Moreover, unsupervised machine learning methods don't require holding out data for validation and testing, making it an efficient approach in many critical situations. In this literature, they applied a high-performance unsupervised machine learning approach to tackle an image classification problem. The basic workflow has four main steps. The first step is pre-processing. In this step, they prepare the image data so that it can be read and processed by a convolutional neural network. The second step is feature extraction. In this step, they use the CNN to generate numerical representation of each image, which helps capture its essential features. Next is dimensionality reduction. After extracting features, they reduce the dimensionality of the data using the principal component analysis, making the problem more computationally efficient. The final step is clustering. They applied K-means clustering to group images based on similar features, allowing us to classify them without any prior labels. For this study, they use the Northeastern University's Data Service Defects Database, NUSSDD, as the training dataset, which is an open source database containing labeled images of various steel defects. This dataset is particularly useful for tasks such as defect classification. The database consists of 1,800 images of the surface defects observed on samples of hot rolled steel. The images are evenly divided into 6 classes, which are inclusions, rolled in scale, patches, squeezing, pitted surface, and scratches. All images are the same size and format, making them very convenient for further analysis. Next, let's detailedly talk about the workflow. After pre-processing the data, they choose to use a process named transfer learning to extract features. Transfer learning means using intermediate layers of a pre-trained CNN to extract meaningful features for images. For the pre-trained CNN, they choose VGG16 network, which was pre-trained on the ImageNet database. They choose this CNN because of its high performance and relative simplicity. And they choose to use the first fully connect layer of the VGG16 to extract features. After feature extraction, they will use the PCA to reduce noise and decrease the computational cost. The number of the components is very important. Using too few components results in a lower classification performance resulting from a loss of useful information in the original features. Using too many components will introduce noise into the features, which will increase the computational requirements of the analysis and also may decrease the performance. For the features used in this experiment, they found using 50 components can preserve 73% of the variance and was found to give the best performance. Therefore, they choose 50 components in this study. The last step in the analysis is clustering, and they choose k-means algorithm for clustering. The basic workflow for k-means shows below. This approach try to minimize the inertia, which is the sum of the squared Euclidean distance from each point to its associated cluster center. There are different approaches for selecting the starting centroids, and in this study, they choose k-means plus plus method, which has been shown good clustering performance and computational efficiency. The next thing is choosing k value. In this study, they choose to use a method named t-distributed stochastic neighbor embedding method, which use a nonlinear transformation to project the high-dimensional data to 2 or 3 dimensions, so that so it can be analyzed visually. On the TSNE maps, points that cluster together in feature space are also likely to cluster together on TSNE maps. This is a sample of TSNE map for the NUSSDD database. From this map, we can find although the database has 6 kind of defect, this map exhibit 1, 2, 3, 4, 5, 6, 7 clusters. Because this method seems horizontal scratches and vertical scratches as different kind of defects, and therefore they choose k equals to 7 in this study during the k-means to maximize the classification performance. Finally, let's discuss the model evaluation. When ground truth class labels are available, clustering algorithms can be assessed based on precision and recall. Precision for class I represents the likelihood that a prediction made by the model for class I is correct. Recall for class I represents the likelihood that a data point belonging to class I will be correctly classified by the model. The evaluation results are illustrated in the figure, where we can observe that for each class of defects, the model achieves precision and recall values greater than 0.98, indicating a high level of accuracy in defect classification. Additionally, the performance of the model can be visualized using a confusion matrix. The diagonal elements in the confusion matrix represent the correctly predict data points, while the off-diagonal elements represent misclassifications. From this confusion matrix, we can find the accuracy is more than 99% on this data set, further confirming the model's high accuracy. In sum, this paper provides a detailed description of the steps required to apply transfer learning to classify images with k-means clustering. This the approach outlined in this study achieved over 99% accuracy, demonstrating improved accuracy compared to prior studies. From this paper, we can also learn how to combine the neural network, PCA, and the k-means together to solve complex computer vision problems. That's all for my presentation. Thank you for listening.